Thank you for having me here today. My name is Giulia. I'm a PhD student at the University of New South Wales in Sydney. And as Carol said, it's late here. It's 11:30 p.m. So please be nice to me. But yeah, anyway, today I'm gonna talk to you about my most recent PhD project that is focused on reconstructing the internal mass distributions and the orbital structures of SAMI passive galaxies using sphere-shield orbit superposition models. Before going into that, Carl already gave you a little bit of context for this, but just let me add to that a little bit. As you know, our current understanding of galaxy formation suggests that galaxies form in a two-phase process. So we have a first phase with in situ star formation, and then we have a second phase redshift after redshift 2-3, where the outer regions start to assemble by accreting stars through mergers and galaxy interactions. Now, evidence of this formation scenario are predicted to be preserved in the stellar population radial profiles and in the stellar 2D kinematics of local galaxies. So for this project in particular, I've been focusing on the stellar 2D kinematics, applying sphere-shield orbit superposition models in order to reproduce the internal structure of galaxies and better understand their merger history. So sphere-shield orbit superposition models are a very powerful technique that allows kinematic substructures in galaxies to be revealed. We separate the kinematic orbits into 4 different components: a cold component with near circular orbits, a hot rotationally supported, a hot component with near radial orbits, so pressure supported, and a warp component in between these two, and a counter-rotating component that is similar to the cold and warm components, but rotating in the opposite direction. So the inferred internal orbital distributions can be used to reconstruct the photometry and the kinematics of each of these components. You can see an example in the picture in the right here. This was done for a galaxy in the Khalifa sample. The same implementation that we use for this work has been previously applied to a sample of Khalifa galaxies by Ling Zhu, and to a sample of Manga galaxies by Jin. We decided to apply these models to a sample of SAMI passive galaxies, and SAMI is a great survey for this because we have a statistically significant number of galaxies in a range of stellar masses and environments. Moreover, we also have information on the higher kinematic moments, such as H3 and H4, that were derived by Condescended in 17. They were not available in the previous studies. So the SAMI Galaxy Survey is an integral field spectroscopy survey and consists of more than 3,000 galaxies in the local universe. Now, since it's integral field spectroscopy survey, we don't have just an image or a spectrum for each observation, but we have a 3D data cube. So we can have specially resolved properties for each galaxy. So that's why we have 2D kinematic maps for each of our observations. After a selection process, we decided to use 124 passive galaxies for our primary sample. And these galaxies have stellar masses that are ranging between 10 to the 9.6 to 10 to the 11.3. Now, we applied spatial models to the observations in order to get the best representation possible for these galaxies. I won't go into the details, but I'm gonna show you one example of the fits that we do. This is just an average galaxy, so it's not one of the best ones that we have. It's not one of the worst ones, but just to give you an idea of how good it can be. So we have the observation maps in the top row. So luminosity distribution going from the left to the right, then line of sight velocity dispersions, H3 and H4. And then the second row is the best fit models created from the spatial code, and the residuals are in the bottom row. So as you can see, the models reproduce quite well the observed maps, although not perfectly, but it's still great. once we find the best fit model, we can reconstruct the internal structure of a galaxy with finding their internal parameters such as the enclosed mass distribution for the total mass profile or stellar mass profile, dark matter profiles, the intrinsic shape of a galaxy, and the fraction of the orbital component. So all of the parameters that we derived are done within one array or at one array, depending on the parameter. I'm not gonna go exploring all the results that we got because it's way too long, but I'm happy to discuss it if you're interested later. But I'm just gonna show you quickly a couple of plots and then focus on the main one that I'm interested in today. So for example, for the whole sample, this is the distribution of dark matter fraction that we got within one array. The data was divided into 5 mass bins, and the crosses that you see are, so these ones, are the median values for each mass bin, and the error bars are delimiting the 1 sigma scatter in the distribution. Now, as you can see, there are error bars that are quite big for some of those galaxies, but the main point here was that the distribution that we found, at least the trend with stellar mass, was similar, the U-shaped trend was similar with those found in literature. Then for the shape, the intrinsic shape of the galaxies, this is the triaxial parameter versus stellar mass. So depending on the value of this parameter, galaxies are classified as oblate, triaxial, or prolate. So as you can see, most of the galaxies are oblate galaxies, but we do see an increase of non-oblate galaxies with increasing stellar mass. This is also clear if we look at this plot on the top panel, where I plotted the diffraction of non-oblate galaxies with increasing stellar mass. The x-axis is the same as below. Again, this is consistent with other results found in literature, and it's quite interesting to see that, that we don't really see many triaxial galaxies below 10 to the 10.7. Then if we look at the distribution of the orbital fraction with stellar mass, so here there are lots of points, so I'm just gonna quickly explain them. The red diamonds are the values of fractions for the hot orbits within one array. Orange circles are the warm orbits, green squares are the counter-rotating orbits, and blue triangles are the cold orbits. Then again, the data was divided into 5 mass bins. That was the same for all of the orbits, same mass bins for all of them. And the bold points show the median value of each of them, with the error bars representing the 1 sigma scatter around the median value. And as you can see, it looks like for galaxies in the stellar masses, they are around 10 to the 10.5, 25.5. They have more or less the same contribution from hot and warm component. While if we look at the trend with increasing stellar mass, we see that the fraction of hot orbits looks like it's increasing, although there's a lot of scatter there, while at the same stellar mass, the warm orbits start to decrease. We don't really see much of a difference for cold and counter-rotating orbits, but what I'm really interested in showing you is this plot. So there's a lot of information in this plot. So first of all, we're just gonna have a look at the distribution of the orbital fraction, the orbital fractions with the spin parameter lambda r, measured at one array. So we have cold orbits here, warm orbits, hot and counter-rotating orbits, without looking at the colors at the moment, for the moment. So you can see that for slow rotators, so with values of lambda r, they are close to 0. The main contribution is given as expected by hot orbits. I say as expected because slow rotators are pressure supported, and their main contribution is given by random motions, and that's what hot orbits are. While if we look at, so that we don't expect them to have strong rotation. So we don't expect them to have huge values of cold orbits or warm orbits. While if we look at galaxies with higher rotation, well, spin parameter, we see that the contribution of the warm component start to increase. And cold orbits are increasing a little bit as well, but not that much. But again, we're looking at passive galaxies, so most of them are elliptical galaxy. So we don't really expect to see strong thin disks components here. So it's good to have this confirmation. But again, these galaxies, they have strong rotation, are rotationally supported, but by warm orbits instead of cold orbits. So this might also be interpreted as evidence that these galaxies have formed mostly through extended minor accretion that started early in their life rather than via a single major merger. Now, if we add the extra information that I plotted here with the colors, so the colors represents different kinematic classes. These kinematic classes were defined by von der Sande 2017 for SAMI galaxies. So high order stellar kinematics, in particular, the V over sigma versus H3 signature were used to classify galaxies into 5 distinct classes. So galaxies belonging to class 1 are the most massive, large, and red. They're plotted as purple here, but they're red galaxies. And as they have complex dynamical structure and they're slow rotators. As you can see here, they're mostly supported by hot orbits. The contours indicate the 68%, so 1 sigma of the distribution for that class, for the galaxies in that class. And then if we look at galaxies in class 2, these galaxies are less massive than galaxies in class 1. They're still red. They reside in between slow and fast rotators. But as you can see, the work components becomes more important for this class compared to class 1, while the hot components is still quite high, but decreasing. We have a wider range, but the cold orbits are still quite low. And same for the counter-rotating orbits, they're not that important. Then if we look at class 3 and class 4, so the orange and green, that I just realized you can't really see that well, sorry. But it's here, yeah, orange and green classes. Those are regular rotators, and they show strong anti-correlation between V over sigma and H3. So as you can see here, they have higher values of warm orbit, thank you, and lower values of hot orbits, while they have a kind of like little bit more value, higher fraction of cold orbits, but not that much. Then if we look at class 5, these are fast rotators again, but they do not show any sign of anti-correlation between V over sigma and H3. They do, however, show sign of disturbances in their kinematics. So before it was thought that one of the hypotheses for this was that there was a counter-rotating component in this galaxy causing disturbances. But then now if we have a look at the counter-rotating component for this galaxy class 5, so the red dots, we do not really see a great contribution from the counter-rotating components. We do, however, see like a little bit, like the values for cold fraction are a little bit higher compared to the other ones, although the main contribution is still from warm orbits and hot orbits. So one of the suggestions that to explain these disturbances in the kinematics is that there is a particular structure in the galaxy, so maybe a strong bar in the center causing the disturbance, the signal in the kinematics, and this is supported by this higher fraction of cold orbits that we have. Now, the other thing that I think is really important to take on from this plot is that we have lots of data that doesn't have the quality to have dynamical models applied to them. So having the extra information about the higher order stellar kinematics can help us to still have a little bit like of a handle inside this galaxy and to understand what's going on in there. For example, if we have galaxies that show they are fast rotators but do not show any correlation, anti-correlation between V over sigma and H3, we can easily well, not easily, but we can have a better understanding of how, like, their fraction of cold orbits, or at least have an idea of what fraction of orbits of each component they have. So this is it for now. I actually have plenty of other results. So if you are interested and you want to discuss it, I'm really happy to do that. But just to summarize, we use partial models to derive the intrinsic properties of galaxies in the SAMI galaxy survey. We found that the most massive galaxies are more likely to be triaxial compared to galaxies of lower mass. And again, these most massive galaxies are pressure supported with a high fraction of hot orbits, while we have the one component that becomes more important for galaxies at lower masses. And then the higher order moments can really help us understand the internal structure of galaxies when modeling is not possible. And I'll leave you with the summary. Thank you again.